This is the architecture of a bidirectional associative memory. This is an associative memory. It associates a pattern. If we give an input pattern, it will identify which pattern it is. It associates a pattern. It is used in character identification, character recognition, image identification. For that purpose, we can use it. You see the architecture of the bidirectional associative memory. We have input neurons in the input layer. We have output neurons. These input and output neurons are connected bidirectional. You see the arrow marks. It is connected in bidirectional way. That means that this layer, X layer, will access input layer as well as an output layer. Similarly, the Y layer, Y neurons access an input neuron as well as the output neuron. That is, we can apply the input here at the input layer while the X is acting as an input neuron, and we can compute the output at the output layer, Y neuron. That time the input signal is applied at X and we are getting the output at Y. Vice versa, it is also possible. That is, we can also apply the input at the Y layer. That time that Y neuron will act as a input neuron, and we have to compute the net input at the X layer. Then we have to apply activation function and we have to calculate the output of the X neuron. That time the X neuron acts as a output neuron and Y neuron acts as an input neuron. So that's why it is called as a bidirectional network, and this network is used for associating the patterns. Hence it is called as bidirectional associative memory network. Now you are seeing the architecture. In this, the weights are connected between X neuron and Y neuron. The first step in this bidirectional associative network is you have to calculate the weight of the value of the weights required to memorize the pattern, to memorize the input patterns, input and output patterns. For calculating the weight matrix, we can use these formulas. That is, for the binary input vectors, the weight map for calculating the weight matrix, you use this formula. This is Wij is equal to summation for all values of P. Your S is the input pattern and T is the target, that is the output for the input pattern. So you have to use this formula for the binary input vector, and for the bipolar input vectors, the weight matrix is calculated using the formula Wij is equal to summation for all values of P, Si of P into Tj of P. S is the input pattern, T is the target pattern. So these are the two formulas you have to use. While you are using this for the real-time application, you will get the more clarity in this. So the activation function that we have to use for this is, if your applied input pattern is binary input vector, you have to use this activation function. That is, your Yj is, that is the output of the jth neuron is, it is equal to 1 if the net input of that neuron is greater than 0 and it is equal to the previous output whatever it has when the net input of that neuron is 0. Equal to 0, and it is equal to 0 if the net input is less than 0. This is for the binary input vector. Then the activation function for the X layer is, this is for the Y layer, and for the X layer is the same way. You have to, if you are going to use the X layer as the output layer, then in such a case you have to use this activation function. If the net input is greater than 0, its output is 1, and it is equal to 0, the output is same as the previous one, and if it is less than 0, output is 0. Then these are the cases for the binary input vectors. Next we are going to see the activation function for the bipolar input vectors. If the applied input vectors are in bipolar nature, then the activation function for the Y layer is the same formula only we are going to use. The output of the jth neuron is, it is equal to 1 if the net input of that neuron is greater than theta j, and if it is equal to the same as the previous output if the net input is equal to theta j, and it is equal to minus 1 if the net input is less than theta j. Then this is the activation function for the X layer, while the X layer is used as the output neuron. This same cases. Then in that cases, the theta value you can assume any value, even you can assume the theta value as 0. So in such a case, you will be getting the output of that neuron that is equal to 1 if it is greater than theta, and it is same as the previous output if it is equal to theta, and if it is less than theta, output is minus 1. Here we are getting the output as 1 and minus 1. Hence it is the bipolar output vectors. Next we are going to see the algorithm for the BAM network. Here I have reproduced the architecture for only two input neuron, two neurons in the input layer and the output layer. Same way this will also act as an input layer, and this will become a output layer in such a case. So this is the algorithm given. In this, first we have to initialize the weights. First we have to find out what are the weight values. That is the first step. Initialize the weights to store a set of p vectors. Initialize all activations to 0. All other values we have to first assume as 0. Then for each testing input, do steps 2 to 6. First, present input pattern X to the X layer. We have to apply the input pattern at the X layer. Then present input pattern to the Y to the Y layer. That is, if you are going to use this layer as an input layer, then in such a case you have to present the input pattern at the Y layer. So first, your first step is, first you are initializing the weight matrix, then you are applying the input pattern. Next, if you are applying the input at the X layer, you have to compute the net input at the neurons. So as we already know, the net input you have to calculate by, if I am calculating the net input of the first output neuron, then it is, you have to see how many signals are coming to that neuron. So it is from X1 one signal is coming, from X2 another signal is coming. So this X1 input signal has to be multiplied by W11 plus X2 input signal is multiplied by W21. That is the net input of the first output neuron. Similar way, you have to calculate the net input of the next neuron. So that is X1 into W12 plus X2 into W22. Like that, you have to calculate all the net input of the output neurons. That is the thing it is mentioned here. It is, you have to compute the net input of the neuron in the Y layer. So it is Yinj is equal to summation for all values of I, Wij into Xi. That is, I is the signal at the input layer. That is, you have to number of neurons in the input layer. So first it is weight matrix into the input, that will give you the net input of that output neuron. Then we have to as usual we have to apply the activation function for the output neuron. So it is output of the first output neuron is function of, we are applying some activation function f of net input. Similar way, this is for if you are using your Y layer as an input layer and X layer as an output layer. In such a case, you have to use, you have to compute, that is, you are applying signal at the input neuron, and you have to calculate the net input in the X layer. For calculating the net input, what you have to do? You have to multiply the signal by the weight. So that is the thing given here. So it is, you are multiplying the signal, that is the input signal that we are applying at the Y layer now. So this is multiplied by the weight vector, that will give you the net input of the X layer. Then we have to apply the activation function. We have to apply the activation function to calculate the output at the X layer, which is Xi is equal to function of X IN I. This is XIN I. Your XIN I is equal to summation for all values of j, that is for all values of j we are doing it, Wij into Yj. So this way you have to calculate the output of the each layer. Okay, that is the algorithm so far we have seen. Then you have to do it if the activation vectors x and y have reached equilibrium, then stop, otherwise we have to continue. This is the algorithm. Now we are going to this is the algorithm for the discrete, that is if your input is binary or bipolar. For that, how to use this BAM network for pattern association, that is given. Then we also have the BAM network for the continuous input signal. So in such a case there are no much difference, only there are difference in the activation function. You see, this is the weight matrix, that is this is using this formula you have to calculate the weight matrix that we have already seen. And this is the formula we have to use it for the activation function. That is, the activation function is, this is the function used for the sigmoidal function. For that activation function you have to use. That is the difference, only difference. Now we are going to see one application using the BAM network. You can see here, these are the characters. These are the character for this is the digital pattern, matrix pattern, which is used to represent character A, and this is the digital pattern used to represent character C. You can see the dark dots which represents character A, and this is character C. Now this character A and character C are represented using 5 cross 3 matrix. You see, 5 rows are there, 3 columns are there. Using this they have represented character A. Now what we are going to do is, we are going to associate the character A with output -1 1. That is, if you are applying the character A at the input layer of the BAM network, the BAM network have to produce the output as -1 and 1. And if you apply character C at the input of the BAM network, the BAM network have to produce the output as 1 and 1. Right? Now these A and C are the two input patterns, input patterns which are going to be applied at the BAM network. And if you apply these characters, that is, if you apply your BAM network is going to store these two patterns A and C in its memory, right? It stores these patterns by means of the weight matrix, right? If you apply character A at the BAM network, your BAM network will produce -1 and 1 as an output. And if you apply character C as an input to the BAM network, the BAM network will produce an output as 1 and 1. So that says that this it has a pattern. The BAM network is identifying the applied input patterns by means of producing another output pattern. Okay, hence it is called as a pattern association network. So it associates a pattern, that is, it is used to help the user to identify which pattern is applied as an input. For that, we are using some representation at the output to identify what is the applied input pattern. Now let us see how this BAM network associates the pattern. Take an example. Now first we are taking the character A. This character A, which is represented by means of this matrix, 5 cross 3 matrix, can be written as a bipolar vector like this. You see this. Now here we are going to assume the circle as -1 and dots as plus 1. Plus 1. In this, the circle has minus 1 and dot has plus 1. So if you write those, if you replace these dots by means of 1 and minus 1, you'll be getting a matrix like this. You see, first you have a circle, so we are writing minus 1. Next you have a dot, so you are writing 1. Like that, for each and every circles, you have to write a digital code, bipolar code. So it is first minus 1, next 1, next you have a circle minus 1, next you have a dot 1, next you have this way dot, next circle dot, 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 circle dot, dot, circle dot. This way you have to go. First row, second row, third row, fourth row, fifth row. All this you have to write it one by one, right? Similarly, so this is the code. This is the bipolar vector input pattern for the character A. For the character A. That's why it is written as SI, right? This is the SI means that is the input pattern. Input pattern for the first character. Next, we are writing for character C. For character C, similar way it is circle, so it is minus 1, next 2 dots, so it is 1, 1, next 1 dot, so it is 1, next 2 circles, so it is minus 1, minus 1. Similar way you have to do it for the all other rows. So now you have got the patterns, bipolar input patterns for the character A and character C. Now our work is, we have a pattern, we have 2 characters. Now your BAM network is going to store these 2 patterns in its architecture. How it is going to store the 2 characters. For that, first we have to find out the weight matrix. The weight matrix required to store the 2 patterns. Already we had seen, if your applied input vectors are bipolar in nature, you have to use the formula for finding out the weight matrix. Wij is equal to summation for all values of P, Si of P, Tj of P. This is the formula you have to use. P means it is a pattern. If you are going to find out the Wij for the first pattern, that is P is 1, you have to take Si of 1 and Tj of 1. Now we are going to do the Wij for the first pattern, which is A. So it is Si of P. Si of P is Si of 1. That is equal to, now the input pattern for the first pattern is, the first pattern is A. For that, it is the input is already given. We have given it by means of the 15 cross 1 matrix. We have written. And the required target for that is Tj of P is, that is we already targeted. If we apply character A, it has to produce minus 1 and 1 as an output. These we have taken 2 bits because we are storing 2 patterns, 2 characters. Hence we have taken 2 bits at the output. If you are going to store 4 patterns, then you can take 4 bits at its output. Now it is 2, so we have taken 2 bits. In that I am going to say it is character A, so first letter first digit I kept 1 and second digit as minus 1. So this is the input pattern, this is the target pattern. This is of 15 cross 1 matrix, this is of 1 cross 2 matrix. Now we are going to find out what is the W matrix required to store this character A. So it is Wij of 1 is equal to, what you have to do, you have to multiply S and T. So you multiply this 15 cross 1 by this 1 cross 2 matrix. So if you multiply these two, you will be getting, how will you multiply? This is minus 1 into minus 1. So it is 1. Then minus 1 into 1. It is minus 1. 1 second row, 1 into minus 1, minus 1. 1 into 1, 1. Like that, each row and column you multiply, you will be getting a matrix which is of 15 cross 2 nature. So this is the W matrix required to store the pattern A. Next we have to find out the W matrix required to store the pattern C. You see this? So for the character C, this is the bipolar vector, input vector. This is the target vector. Now the target vector is, we are keeping 1 and 1 as an output for the character C. Now we have to find out the weight matrix for storing the character C. So for that you have to multiply the input vector by the target vector S into T. So if you multiply these two vectors, you will be getting the weight matrix like this. So this is the weight matrix to store the character C. Now you have to, the final weight matrix is, you have to add the weight matrix for each characters. So this is the weight matrix for the character A, this is the weight matrix for the character C. These two matrices you have to add, then you will be getting the final weight of the BAM network. You see this. So this is the final weight matrix of the BAM network. Now this weight matrix, what it represents, where it has to take its value. You can refer this. So now I am going to apply the characters patterns, that is A or C, whatever it is, at the X layer as an input, and I'll be getting the output at the Y layer. Now my input pattern consists of 15 bits. So I have to take 15 neurons, X1 to X15. And my output pattern consists of 2 bits. So I have taken Y1 and Y2, 2 neurons at the output layer. Now I have to connect each input neuron with the output neuron by means of bidirectional paths. So it is bidirectional, both way the arrows. These bidirectional path is connected by the weight matrix. This is W11 connects first neuron to the first output neuron. This is W21 connects second input neuron with the first output neuron. Like that we have to name it first. Then these values you can write it here. So you see this is W11, this is W12. So W11 is 0, W12 is minus 2, W12, this is minus 2. Next W21 is 0, W22 is 2, W21 it is 0, W22 is 2, W22 it is 2. Like this you have to write the values of the weight matrix in the architecture, right? So this is W1112, 2122, 3132, 4142, like that. 151, 15, 151, 151, 152. So we had written the weight matrix. Now we have to calculate. Now we have applied the input pattern first, that is character A, first input pattern we have applied at the X layer. We have computed what is the weight matrix required to store the patterns A and C already. This is the weight matrix required to store pattern A as well as pattern C. That weight matrix we have replaced. Then now we are calculating what is the output if we apply this input pattern. So to calculate the output, first we have to calculate the net input of the output neuron 1. So you have to calculate the net input using this formula. Yin1 is equal to, first the net input of the first neuron is summation for all values of I, xi, wij. This is for all values of I. Summation for all values of I, xi, wij. So you have to, first you can take xi, is1, so it is x1, w, js. Now we are calculating the net input of the first neuron, so js1 always. So it is x1, w11. Next we have to take is2, second input neuron. So it is, if I take is2, it is x2, w21, x2, w21. Then x3, w31. x4, w41, etc. till x15, w151. So all the input bits you have to multiply by the respective weights and have to sum it. If you sum that, you'll be getting the net input of the first output neuron. So that way you have to calculate the net input of this neuron, the net input of the second neuron that we had written here. So this is the weight matrix is already there. We have applied the input pattern. So we are multiplying the input bits with the weights. So it is, you are getting, you see. So first for the character A, it is -1, 1, -1. So I have written here -1, x2 as 1, x3 as -1, okay, x4 as 1, x4 as 1, like that, x15 as 1. Then this weight matrix already we have replaced. Then we are multiplying this by -1 into, already the value was here 0, -1 into 0, then plus 1 into 0, plus -1 into 2, okay. So if you refer this, -1 into 0, 0, next 1 into 0, 0, next -1 into, this is x3 is -1, -1 into 2, the weight is 2, so you'll be getting -2. Like that you have to compute what is the net input of the first neuron. For this you have to, you can take this bits and JS1, this is so this is this net input, you can multiply by the respective weights, then you have to sum it, you'll be getting this net input of the first neuron. So if you add this, you'll be getting net input is equal to -14. Now you have calculated the net input, you have to apply the activation function to find out the what is output. So the net input of the first output neuron, we are getting -14. Similar way you have to calculate the net input of the second output neuron, then you'll be getting 16. You have to apply the activation function for both the inputs. Again for the review we are giving the net activation function is, the output is equal to 1 if net input is greater than theta, and it is equal to the value of the previous value if it is equal to theta, and less than theta if the net input is less than theta, it is -1. Now we are assuming theta as 0. If you apply this activation function, you will be getting, you see, first for the first net input, for the first output neuron, your yj is equal to, it is equal to 1 if your net input is greater than 0, but my net input is -14, which case it will come as, you see, it is -14, so it will fall in the third category, that is -14 is less than or less than 0, so your output will be equal to -1. Then for the second neuron, the net input is 16, it fall in the first category, so your output will be equal to 1. So your output of the first output neuron is -1, second output neuron is 1. So your output pattern is, target is -1, 1. We have applied the character A, we are getting the output as -1, 1. That says that if I can apply, I can store n number of patterns using BAM network, and for each pattern I have to fix some target. Then after that, if I apply, if my input is unknown, and if I am applying that input as an input to the BAM network, and if I am getting that particular target pattern, then I can, from the target, from what is the output I am getting, from that I can conclude that this might be the applied input pattern. Take an example, I don't know whether my applied input pattern is A or C. I have applied some input. If the BAM network produces 1 and 1, 1, 1 as an output, if it produces 1 and 1, 1, 1, then that says that the applied input is C. If the BAM network produces -1, 1, then that says that the applied input is A. So this way we can identify the patterns, applied patterns. You see, the similar way we have repeated it for character C. So for the character C, this is the bipolar input vector, this is the weight matrix. You have to first compute the net input of the first neuron, net input of the second neuron. Then we have to apply the activation function, then have to calculate what is the output. It comes as 1 and 1. So now you are getting 1 and 1 for the applied character C. So in this case we have applied input at the X layer. We have applied input at the X layer and we have calculated the target at the Y layer. The reverse is also possible. You can apply, if you are taking Y as an input layer, you have to apply, if you apply -1, 1, -1 at the Y1 and 1 at the Y2, then what will be getting? Similar way you have to compute that is the weight matrix already we have arrived with. The same weight matrix you can use. Then you have to compute the net input of the X neurons. After computing the net input, you have to apply the activation function. You have to calculate the output. If you do in that way, you'll be getting, if I am applying -1, 1 as a input at the Y layer, I'll be getting character A at the output. That is for the character A, these are the bipolar input vectors you'll be getting. So this output, this bipolar vector, you'll be getting at this layer. So in such a case, this layer Y layer acts as an input layer and X layer acts as an output layer. So this network uses two layers which can be used as both as an input layer as well as an output layer. Hence it is called as a bidirectional associative memory.